Alright, in this video, in section 13.2, we're going to talk about a really powerful way to help us visualize surfaces, referred to as level curves. So we'll start with question number 3 here. It says to sketch the graph of the function f of xy is x squared plus y squared. And first I'm just going to emphasize that this equation is equivalent to saying z is equal to x squared plus y squared. Okay, so if I want to say know what's going on with our surface in three-dimensional space, say in the xz plane. So in other words, if I set y to 0, what I'm going to see here is that z is equal to just x squared, right, which is just a nice parabola. Okay, so this has a special name. So here what I'm going to do is set y to 0, and this parabola we're going to get is what's called the xz trace. It's just the intersection of our surface with the xz plane. Okay, so here, just to help us kind of see how the picture I'm going to draw here pairs up with the 3D picture, I'm going to draw the right branch here as solid and then this left branch here as a dashed portion of the curve. Okay, and then let's go ahead and do the same thing by setting x to 0. This would give us what we're going to call the yz trace. So this would just be z is equal to y squared. So I'll do that same thing here. So there's the right branch and then the left branch. Okay, so then coming back over here, right, we can go ahead and say, all right, how does this xz trace then show up in our three-dimensional picture? Well, for the solid branch, that's going to be out here, and then this is going to be that dashed branch. And this parabola here lives in the xz plane. All right, cool. And then same thing for the yz trace. We're going to get this solid portion out here, and then the dashed part is going to be out there. All right, cool. So now what's going on, say, parallel to the xy plane, right? Well, this has a special name. Okay, this is what we're going to call the level curves of the function. You can think about it as asking, well, if I fix, say, an altitude, right, what are all points on my surface at that altitude? Okay, so we're going to go ahead and set f of xy equal to some constant. So in other words, just z is a constant. And for this particular function, this would translate to saying that, well, x squared plus y squared, because that's our f of xy, is equal to c, right? And notice this is just, if I rewrite the right-hand side, this is just a circle of radius root c. And this also, by the way, puts a certain restriction on c. c here's got to be non-negative, right, in order for this thing to be real valued. So here we're getting, right, a circle of radius square root of c. Okay, so for some examples here, like if c is 0, we're just going to get x squared plus y squared is 0, which you could think of as like a circle of 0 radius. It's really just a single point, right? The only xy pair that makes this true is when both x and y are 0. So in other words, we just get the origin there. So there's that. If we set c to 1, well, we would just get x squared plus y squared is 1. And this is just the unit circle, right? So go ahead and put that in here in a second. And we can just keep going, right? So taking, say, unit steps in C is going to give us a circle centered at the origin whose radius, right, is growing as the square root of whatever C is, okay? So here's what the graphs of these things look like. All right, so when c is 0, we just get the origin. When c is 1, there's our unit circle. When c is 2, that's a circle of radius root 2, and then we would go to a radius of root 3, then a radius of root 4, or in other words 2, and so on and so forth. Okay. All right, so let's come over here now and see how these relate to our three-dimensional picture, right? So what we're looking at, right, are the various cutouts of our surface at various fixed altitudes. So when c is 0, we're just saying, okay, in the xy plane itself, right, our surface will intersect the xy plane in only a single point, right here at the origin. Okay. Now, if we go up to an altitude of 1, right, we're going to cut out the unit circle. So this is when c is 1. You go up another step, and you're going to get a circle of radius root 2. Then go up another step, and you're going to get a circle of radius root 3, and so on and so forth, okay? So this is a nice picture of our surface, okay? Now one comment here, notice on this picture of the level curves, we see that the circles are bunching up, right? The radius growing as the square root of c, right, says that, well, if I take equal steps in c, so over here it says, that translates to just taking equal steps in your altitude, right? The corresponding cutout there on your surface is going to be a circle, right, of radius root c, right? And so you're going to see this bunching up. And that makes sense given this concave up shapes of these parabolic trace curves, right? It's just saying, well, our surface is getting steeper, right, as we increase our altitude, okay? All right, cool. So now let's go ahead and name this thing. This is what's commonly referred to as a circular paraboloid. Okay. And what I'd like to do now is just look at a few graphs here. And just fill out a few more details, so that basically just go through the same things for the same function that we just did, but just this will make it a little more vivid. So right now I've just drawn in the level curves there, and we can see the spacing that I just commented on. Right, we move further out, the circles get tighter and tighter. Okay, and so then what we did was we put in our xz trace and then our yz trace there. Right? And then what we said was, all right, well, if we take, say, the intersection of our surface with, say, a given plane, something like this, okay, what we're going to get is just, right, a circle, a circular cross-section here. And by just changing our altitude, right, we're getting this concentric family of circles. Okay, so you put that all together and we get this nice parabolic bowl-shaped surface. Okay, and as I said, you know, you could think about this red contour up there on the surface as like the intersection of plane z is equal to c and our blue surface there. Okay, so that's a kind of another way to think about it. But yeah, so very nice visual in terms of just understanding the general shape of this thing. Okay, cool. Now what I'd like to do lastly is to go ahead and just define level curves more generally, and then that's going to do it for this video. Okay, so here we're going to go ahead and consider some surface, right? Z is equal to f of xy, and we're going to call the level curves of the surface to be the curves in the xy plane. F of xy is equal to c, okay? And a way to think about this, it's much like what a what a surveyor would do if they wanted to say make a topographic map of a mountain, right? They would say this is a curve at a constant altitude. So, you know, if I want to say I'm on this hillside and I want to walk along some path so my altitude does not change, well, then I should walk along what we're going to call this red contour curve, right? All points on this curve are at the same altitude. Now, if I project that curve down onto the xy plane, that's what we're calling the level curve of the surface, okay, at that altitude. And then if you uh, put this all together for various altitudes, you're going to get a map like this, right? And we'll call this thing a topographic map, right? And as I said in the last example, right, when you see closely spaced contours, it's telling you, right, that you're seeing rapid changes in elevation. Basically, you just don't have to move as far to get that equal change in elevation, right, if the contours are really close. Whereas if you have a large gap, that's telling you you have to cover a greater distance to achieve that same change in altitude. Okay, so this is a good place to stop. In the next couple videos, we're going to look at a lot more on level curves. All right, great.